Someone should remind me if I don't start recording. Okay. So the no cloning theorem is due to Sters and Zurek. This is a Nature paper, 1982. I'm sure if you Google this, you will get the paper. Like I said, I'll post a bunch of these papers, the teleportation and the no cloning paper on Moodle, hopefully by this weekend. Okay, so the no cloning theorem states that arbitrary quantum state cannot be copied perfectly, okay? Or there does not exist a universal quantum cloning machine or a quantum copying machine. Again, I should add the word perfect here, okay? Now, in the initial days of quantum information, people were not talking about perfect and imperfect because the idea from classical information that we have is that classical information can indeed be copied and can be copied perfectly, right? The whole perfect versus imperfect question doesn't even arise so much in the classical case. We have excellent copying machines, right? But in the quantum case, while the no cloning theorem is in 1982, about 10 years later, people realized that if you drop the demand of perfect cloning, you can construct unitary operations which will make approximate copies, right? Anyway, that's a whole subject of research now and so on. So we'll not get into that, but I just want to prove the very simple and elegant proof. So I just want to show you exactly how this was proved. Now, note that any quantum circuit, so if I say that this is a quantum copying circuit, this must be a unitary transformation, right? And it involves two registers, right? I think I wrote this as ket 0 yesterday, but it need not be ket 0. This is some ancilla state, like I said. This is also called a target state sometimes. This is, in essence, the blank paper onto which you copy the information, right? This is the information which is to be copied. So this is sometimes called the data state or the data qubit. Of course, you need not restrict, like I said, this need not be just qubit systems. This could be any arbitrary dimension quantum system. So let me call this the data state. This is the state to be copied, right? And the output of this two register cloning circuit or cloning machine should basically have two copies of the state size. Like I said, you don't want to destroy the original copy, right? Like I said, yeah, so no one's going to give you their notes for copying if you tell them that every time I copy, I'm going to destroy your notes, right? So this state has to be as such unaffected, and instead this ancilla state should be thrown into the state size, right? So this is what we require from an ideal copying circuit. So now, suppose this copying machine works for two states, two data states, let me say. Psi and phi. Okay. Was there a question? So now, what does it mean? It means that I have the initial state is psi tensor S. After the action of this U, it has to become psi tensor psi. I have phi tensor S, and after the action of U, it has to become phi tensor phi, right? Of course, you want it to work for any arbitrary state, but I'm just saying let's assume for starters that it works for two states. And we'll already see the constraint that unitarity imposes, right? So what does this imply now? So let me now take the inner product of, so let me now take the inner product of these two output states, right? So, I don't know, I can call them as, so let me use A, B as the registers, okay? I want to label the registers. And then, so let me do this. So let me take the inner product of this psi psi with phi phi, right? So this basically is inner product psi phi the whole squared, right? But this is also, because this state is the output of the cloning machine acting on psi tensor S, this is the same as taking the inner product of psi S U dagger U psi S, okay? Where this is B, A, B. So I hope you see that. So consider the inner product of this pair of output states you get from acting, basically the output of the copying machine for two different inputs, right? That is simply the inner product of these two states squared. Now if I rewrite, so this step essentially comes from the fact that you can write psi psi as U acting on psi S, right? So it is implied that this U is a unitary that's acting on a pair of qubit registers or quantum registers. So this is UAB, right? So this is UAB acting on psi ASB, and this is also AB, right? So then you see that this, sorry, this is phi, right? So then you see that because U dagger U is identity, right? This then is simply psi S inner product with phi S, right? So the inner product of S with itself is 1. So this is simply then psi phi, right? So I'm taking the inner product of the output and evaluating that in two ways. One way simply gives me inner product psi phi the whole square. The other way gives me psi phi, right? So now this then means that this is putting some constraint on the pair of states that this machine can copy. But what does this imply about the state? What does this equation tell you about the pair of states?
Here psi tensor phi is equal to 1 or 0. They are equal.
Correct. Good. So either psi phi is 0, the inner product of psi with phi is 0, or the inner product of psi with phi must be 1, right? So this is a constraint on the data qubits that can be copied by you. Now you can imagine doing this for many states, right? And what this means, so further, what does this mean? That psi phi must either be orthogonal states, right? or psi is equal to phi, right? Because that's the nature of this inner product. It is 0, rather it is 1 if and only if the state is the same, right? So it is 0 if and only if the states are orthogonal, right? So what this tells us is if you impose the constraint of unitarity, right, that your quantum copying circuit must be a unitary circuit, and you want to make perfect copies of multiple states, then those multiple states must be orthogonal, or you can devise a copying machine which is specific to a given state, right? That of course does not help anybody's cause. So the bottom line is that you cannot have an arbitrary universal quantum copying machine, right? So these states which are orthogonal are essentially what we call classical states. Why do we say that? Because they can be distinguished perfectly. Remember that whole discussion we have had several weeks ago about how orthogonal states can be distinguished perfectly, but non-orthogonal states cannot be distinguished perfectly. They can be copied perfectly. So a set of orthogonal states are in some sense a limit in this space of quantum states, in the state space, because they essentially behave like classical states. You can devise measurements to discriminate them perfectly. You can copy them perfectly, right? Whereas it's the non-orthogonal states which show interesting quantum properties, like the fact that they cannot be distinguished perfectly. There is no measurement you can devise which you can with which you can distinguish them perfectly. There is no copying machine that you can construct using which they can be copied perfectly, right? Okay, so any questions? No? The argument is clear? Okay, so what I wanted to do next was to talk about something called the reduced density operator, right? We've discussed now entanglement. We've discussed specifically bipartite entanglement. I've really not shown you multi-party entanglement. We will maybe briefly do that next week. But even within bipartite entanglement, we haven't discussed what is the local description of an entangled state or any bipartite quantum state for that matter. The next idea that I want to discuss is that of the reduced density operator. Okay, so suppose I have a two-party quantum system. So suppose I have a bipartite quantum state. And now I'm talking in terms of a density operator, most generally, right, of the form rho AB. Okay, so I introduced bipartite states maybe as of this form, right, where I said psi AB, the most general state is of the form A00 plus B01. So let's say qubit, for example, okay, C10 plus B11. Correspondingly, I can write down bipartite density operator, right? So this would be a pure bipartite state. Now I can also write down mixed bipartite states, right? Which basically is a 2-qubit density operator. That's what I want to write down. So this would essentially be some mixture of such pure bipartite states, right? The single qubit case or the single quantum system case was the same, right? If I have a set of pure states which are drawn according to some probability distribution Pi, then this sum of the outer products on the sum of the projectors onto those pure states weighted by these probabilities is what describes the density operator, right? So the idea is the same, right? So this is what this is how I would represent a bipartite density operator. In the case of a 2-qubit density operator, what would be the dimensionality of this matrix? So remember that these are matrix representations, right? Yeah. Sorry?
16, ma'am.
16. What does that mean? It's a matrix. So you have to tell me how many rows, how many columns.
4 cross 4.
Okay. So telling me the number of entries. Okay, good. So 4 cross 4. So this will be a 4 cross 4 matrix. Okay. So maybe just as a simple exercise, let's do this example. So let me say that I have first just one Bell state. So consider beta 0, 0, right? Which is 1 over root 2, 0, 0 plus 1, 1. Okay. So firstly, what is the 4 vector description of this? So what is the state description of this? And then what is the density matrix description of this? Okay. So you guys are going to tell me this. So remember that your starting point is that if you want to start there, you can start there, which is a 0 is 1, 0 and 1 is 0, 1. So you know what 0 tensor 0 is. We wrote down all of this, right? You know what 1, 1 is. So use this and tell me. So this is going to be some column vector, right? This is a pure state. So it's going to be some column vector with 4 entries. So what is this column vector?
1001 scaled by 1 by root 2.
Very good. So this is 1 over root 2, 1001. If you want, you can write it as 1 over root 2, 0, 0, 1 over root 2. All right. Now tell me, what is the projector onto the Bell state, which essentially is what we would call the density operator associated with the Bell state, right? So what is this? We just discussed that this has to be a 4 cross 4 matrix. So I want the entries of this 4 cross 4 matrix.
No, 1 0 0 1 and then 2 rows of zeros and again 1 0 0.
Very good. So this is the 4 cross 4 matrix you will get. It is indeed a very sparse matrix, right? That's what is special about these entangled states. You see, it has support only on 0, 0 and 1, 1. So when you take the outer product, only those cross terms will figure. So essentially, you have only these 4 entries on the edges, right? And then you have this. So anyway, now you can construct truly mixed states. Okay, so this was a pure state actually, right? Bipartite pure state. I just wanted you to see the vector and the matrix description. Now let's do a genuine mixed state. So rho AB could be
Ma'am,
an
will there
equal.
be a factor of half?
Oops, yes, 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 yes. We got carried away. Of course, there's a factor of half. Thanks. Yeah. So let's say we have an equal mixture of 2 Bell states. Actually, let's first do an equal mixture of 2 product states of 0, 0 and 1, 1. Okay. So how would you represent this? This would be half outer product 0, 0 plus half outer product 1, 1. Correct? So what is this density matrix? So this is the ensemble. It should be given as half 0, 0, 0, 0 and half 1, 1, 1, 1. Yeah. Yes. Why is this taking so long? You wrote down the Bell state. You told me the Bell state quickly enough.
Ma'am, only the upper and the lower most elements will be 1. I mean, diagonally, rest all zeros.
Correct. Very good. So this is essentially a diagonal matrix, right? Yeah, I see Sumit is actually typing out the answer on chat. Thank you. Okay, so we have these 2 rows of zeros, right? Like with the state that we wrote down corresponding to the Bell state, right? But notice that now you no longer have the off-diagonal element, right? So I hope you understand why I made you do these 2 particular examples. Okay. Someone asked me yesterday about Neelkant, right? Coherent versus incoherent. Okay. So I kept saying that the Bell state is a coherent superposition of 0 and 1, right? So this is the density matrix that's associated with that. And you notice these 2 off-diagonal elements sitting here. Whereas if I simply take an incoherent mixture of 0, 0 and 1, 1, this is what I get. There are no off-diagonal terms, right? These off-diagonal terms are in fact what carry relative phase information. And this is what distinguishes a mixture of 0, 0 and 1, 1 from a superposition of 0, 0 and 1, 1, right? This first example we did is the density matrix associated with the superposition of equal superposition of 0, 0 and 1, 1. And this is, of course, I don't know whether I should have done this exercise for a single qubit as well, and you would have observed the same thing, right? So if I did not do this, then please do this example where I have row A, this is just a single qubit, right? One is where it is basically of the form psi psi, where psi is an equal superposition of 0 and 1, right? And the other, so I'll call this rho A tilde, where it's simply an equal mixture of 0, 0 and 1, 1. Okay. So again, you will notice the same difference, that you will have these off-diagonal terms whenever you have this coherent superposition. The density matrix is the coherent superposition. And in fact, it is these off-diagonals which will decay typically when you have what is called decoherence. Right? So decoherence is basically when you lose information about these off-diagonal elements. Okay, so now I hope you're comfortable with writing down bipartite density matrices as well, right? So bipartite pure state, bipartite mixed state, okay? And also entangled bipartite pure state, right? Rho AB is a density matrix associated with an entangled state, right? I've not yet made a mixture of that, but what we can do next is also to do this. Okay, maybe I'll do that a bit later because I want to now talk about reduced density matrix. So let me do that first. All right, so we have a general bipartite state now, and I'm going to start writing down a density matrix as the most general bipartite state that I can write down, right? Okay, maybe I'll just give you this one example, non-trivial example. So you can, just like you had an equal mixture of 0, 0 and 1, 1, you can think of an equal mixture of 2 Bell states. Okay, so maybe just work this out for me. This is the last, so I'll call it some sigma AB, okay? And this is an equal mixture of beta 0, 0 and beta 0, 1. Okay, what was beta 0, 1 now? Yes? What was beta 0, 1? Anybody? Okay, I claim that it is 0, 1 plus 1, 0. Okay. All right, you can go back and check, but this is what I think it is. So now, can you tell me what this density matrix will look like? This is now an equal mixture of two bell states, right? So essentially, it's the ensemble corresponding to the bell state beta 0, 0 being prepared with probability half, and the bell state beta 0, 1 being prepared with probability half. Okay. So what is this matrix?
Zero one one zero.
0. What do you mean? I didn't understand.
Um, 1001, 0110,
Yes.
0110, and again 1001, and a factor of half outside.
Wait. 1001 and then
0110,
correct.
and then again 0110.
Very good. Yes. Okay. Is it a factor of half outside?
Yes, ma'am.
Sure. Don't the bell states have a factor of 1 over root 2 themselves? And then you're taking an equal mixture. See, it's easy for me to tell you that your answer is wrong if you have a half outside. Why is that?
Trace.
What is the trace?
Yeah, it should be 1 by 4.
Okay, good. So you see now these matrices start looking more and more, they're not as sparse. You start populating more entries. But you notice one thing, that this matrix has an interesting structure. So this, I just write this out here. So all these other entries here are all 0, right? It has populated all the diagonals and exactly all the off diagonals, right? So this is what is called an X structure, okay? So sometimes these are called X matrices, okay, in the literature. And in fact, you will find that you can take an equal mixture of all 4 bell states, right? And you will still end up with an X structure like this. Let's say that, yeah. Well, okay, so you can check that out, right, and see if you get this X structure, right? Take all 4 bell states, do an equal mixture and check. But anyway, now you know that you can have, we have discussed all possibilities really, right? Pure entangled, this is truly a mixed entangled state, right? It is a mixture of 2 pure entangled states, right? And then you have this density matrix associated with a single entangled state, and then you have a density matrix associated with a mixture of 2 product states. Okay, now what is this business of the reduced density matrix? So now consider a general, okay, I hope everyone has worked out these matrices. Please do so. This is important for you to know how to go from the bracket to the matrix notation. Okay. All right. So now let's have a general bipartite state, rho AB, which belongs to some pair of quantum systems represented by Hilbert spaces HA and HP, right? Now I want to know what is the local description of this state. Okay, so a more practical way of saying this is, if indeed I have these 2 people, Anita and Bharat, and they manage to share a bell pair, for example, or any entangled state, right? We have written down the global description of the state, right? So what we write down here, this is the global description. This is what the joint 2-qubit state looks like, right? But I want to know, what does the local description really look like? What are the states? If someone were to ask Anita, what is the state that you have? Not the bipartite global state, but what is the local state in your lab? How would one describe that, right? And is there a formal way of describing this for any bipartite, or then of course extended to multi-party state, right? The formal way of doing this is by an operation called the partial trace. Okay, so now let's say that I is some orthonormal basis for the system HA, and J is some orthonormal basis for B, now you can take a partial trace either of subsystem A or of subsystem B, right? If I take a partial, so if I want to know what is the local state on A, it is given by some rho A, right? Most generally, it will be a density operator. It will be a mixed state, right? Which is obtained as, so the formal way of writing it is to say trace over B rho AB, okay? You know the standard trace operation, right? What is trace rho AB? That will be sum over I and J, right? Because the complete orthonormal basis for the bipartite system is now IA tensor JB, right? So if I want to take the trace on the whole system, that is going to be of this form, right? Okay, this is what the full trace will look like, where you are tracing out over both the systems, and this should give me a number, or in this case density operator, so it has to give me 1, but this is a number, right? This has to give me a number at the end of the day. But here I'm telling you that there is an operation called the partial trace, which is giving me an operator in A, because you're only tracing out over the degrees of freedom in B. You're only tracing out over the orthonormal basis in B, right? So this will now look like sum over J okay. So this, you can take this as a kind of formal definition of the partial trace, right? And this is what would be called the reduced density operator, or the marginal density operator, or the marginal state. Again, those of you who are familiar with a bit of probability theory should see the analogy between this and taking the marginal of a joint probability distribution. You can make this analogy very formal, okay, by invoking measures on these operator spaces and so on. We are not going to do that in this course, but I just want to point out that doing this partial trace operation and getting the marginal state or the reduced density operator out is exactly like taking a joint probability distribution Pij and summing over J gives you Pi, which is the distribution over 1, which is one of the marginals of this joint distribution, right? So if I have two random variables A and B, and they're distributed according to this jointly distributed as Pij, you know how to get the marginals out of that, right? So it's exactly like that. Okay, except you do now doing this on operators, and yeah, the operation is somewhat more complicated now. It's what's called a partial trace. Similarly, you can write down the local state on B. And this is simply call this row B, which is now trace over A of this joint bipartite state, right? And that's exactly like getting the other marginal of your joint probability distribution, right? So then this formally you can write it as now sum over I row AB I. Okay. So I hope the definition is clear. Again, let's just do a few examples of this so that we get a handle on this partial trace operation. So the simplest example to do is this, a bipartite product state. Okay. So what is the reduced density operator on A for this bipartite product state? Yes. Do you need to do a
Psi
partial
A
trace and tell me, or can you just? Good. So even without the partial, doing this partial trace and all that, you should be able to tell me. So what are we saying? We're saying that these two people or these two labs or these two systems are basically sharing a product state, right? I mean, they're not sharing, but the state, the joint state is simply a product state. So it's psi A, psi B. The probability analogy of this would be what? What would be the probability, the analogy in the probability sense? It's like the joint distribution Pij's of the form.
Pi times Pj.
Exactly. So this is of the form Pi Pj. So now you don't need to do a marginal. You don't need to do sum over, or more generally you will do an integral. You don't need to do all that. You can just read off, right? You can tell me what the individual distributions are. You can tell me what the marginals are. Similarly, here I have a product state. I didn't want to erase that, so let me keep that. So this is what it should be, right? It should simply be this, and the reduced density matrix on system B should simply be 5, 5. Okay, I'll drop the subsystems wherever it's not, the labels wherever it's not necessary. But we can formally now show this using the partial trace as well. Okay, so what is the joint density matrix now corresponding to this bipartite product state? So how will I write this? So I have psi A, psi B, outer product, psi A, psi B, right? Note that the tensor product is here, correct? So the rules of the Kronecker product or the tensor product tell you that this is exactly the same as psi A, tensor phi B, phi B. Is this clear? Is this step clear to everyone? Please note this, because you know this is the first step in identifying what the joint density operator is, and then what the marginal state is. So you're taking an outer product of a product form, right? It's like taking outer product 0, 0, 0, 0. What is this? This is nothing but 0, 0 outer product in A, tensor 0, 0 outer product in B, right? So that's exactly what I'm doing here. I'm saying this is psi outer product in A, Because as we discussed, whether inner product or outer product, you have to do it within each subsystem, right? And then you take the Kronecker product of whatever it is across the two subsystems. Okay? Now it should become clear that the marginals, indeed, you do get the correct marginals, because what is the state in A? It is trace over B of row AB, right? And that is trace over B of outer product psi psi tensor outer product phi phi, right? But it's only a trace over B now. So this should remain unaffected. And this is a pure state in B. This is a projector onto a pure state in B, so its trace is 1, right? So this is simply psi psi trace of phi phi. Okay, it's a very simple example. I'm just going over the steps because this is what you have to do for more complicated examples that you may encounter, right? But this is, of course, 1. So this is nothing but outer product psi psi. So similarly, I hope you can work out that the reduced density matrix on B is trace over A of row AB, and this is nothing but phi phi. Okay. So for a bipartite product state, it's easy to read off what the local states are, because indeed it is simply a product of two local states. Okay. This example clear? Okay. So moving on, let's do a bipartite product mixed state, not pure state. What would that be? So that is of the form rho A tensor sigma B. So there is some local density operator on A, there is some local density operator on B, and I've simply taken the tensor product of this. This is the most general product state, right? The most general product state is not a pure state of this form. It's not a tensor product of pure states of this form. It's a tensor product of mixed states. And you know how to do the Kronecker product for two matrices. We discussed this the day we defined the Kronecker product or the outer product. Right? It's again like taking a block multiplication. Take every entry of the first matrix and multiply with the second. The second matrix just appears as a block, right? So now again, it should be easy to see. Well, what is the local state? What are the local states? It's even easier to read this off, right? Yes. So the reduced states. Yeah, indeed. The reduced states are simply rho A and sigma B. Okay. So nothing much to do here. So now let's start looking at interesting examples. So I want to look at a bipartite entangled state, and I will stop once we do this example. So this is beta 0, 0, my favorite Bell state. Okay. So now you have to tell me what are the marginal states. So what is rho A? So the joint state is now like this. The joint density operator right? Is that right? No. There must be 4 terms, right? So the joint density operator is basically beta 0, 0, beta 0, 0, right? So this is 1 over root 2, outer product of this with itself. So this is what I should get. I should have 4 terms with an overall factor of half. Now, what are the marginals or the reduced states? So can you now do the partial trace over B and tell me what the reduced state on A is?
Identity by 2.
Very good. So this indeed will turn out to be half 0, 0 plus half 1, 1. And what about the reduced state on B?
Same.
So this is again a key signature of an entangled state, indeed of a maximally entangled state. The reduced density operators are maximally mixed states. Because they are simply identity by 2, whereas the bipartite state is an entangled pure state, right? It's entangled no doubt, but it's a pure state. So we started out with something which is a pure state on the joint system, and we try to evaluate the marginals, you get maximally mixed states. If you were to think of a classical probability analogy, it's as if the joint distribution is like a delta distribution, right? It's a pure state. But the marginals are like uniform distribution, maximally mixed. Okay, so of course this has no analogy in the classical world. Anyway, we'll discuss more on this. So please work this out. I know that everyone has not yet worked this out, so please work out this partial trace. And if you have difficulty, please tell me on Monday, because you should know how to go from this joint bipartite operator to the reduced operators, the reduced density operator. Okay, so I'll stop here.
Excuse me, ma'am.
Yeah.
Ma'am, I mean, when you define the trace, partial trace as expectation value of the density of matrix at with respect to some system. So in that case, I mean, how are you rearranging the orders of the states? Of the ones which are not in the product form.
I didn't understand the question. So I'm not taking expectation value, right? I'm saying I'm taking the diagonal elements in some sense, right? So yeah, you can think of it as an expectation value in specific basis states, and then I'm summing over. But you see, this is not a number. If I just look at one term in that partial trace definition, if I just say I rho AB I, this is not a number, because this is effectively like saying rho AB is a joint state, right? It's like saying I'm taking some kind of inner product, like a partial inner product, but then it's giving me another operator, right? So if I say this is A, right? So then it's as if there is a tensor identity in B that's kind of tagging along with it, right? So it's only the A part where you're taking an expectation in some sense. The B part is unaffected, so that's still an operator. So this should give me rather an operator on B. So you can do this example, no? So when I have 0, 0, 0, 0, right? And then if I take 0, 0 on both sides, what do I get? With respect to either A or B, doesn't matter. I should still get 0, 0 on B, right? So I don't understand what your question was about the order. I mean, there is no.
Yeah, ma'am, that's what I'm trying to say. Like in this case, when you took the zero zero term in the density of the equation that you just wrote. So in that zero zero state, I mean, one is of the A and the other is of the B. So I am actually getting confused that how are you rearranging the orders of the inner states in order to write the
I'm not rearranging. Okay, so your doubt is if I have something like 0, 1, right? I'm not rearranging. What this notation means is 0 tensor 1, right? This is AB. 0, tensor 1. Again, this is AB. Correct? That's what this means, right? 0, 1 means 0, tensor 1. This is the ket, this is the bra,
Yes, ma'am. Yes,
right?
ma'am.
So now, what is your question? There's no question of rearranging anything. I can only take an outer product within each subsystem, right? It doesn't make sense for me to write 0A, 1B. What does that even mean?
Okay, okay. Yeah, I got it, ma'am.
You just have to keep
Yeah.
track of the subsystem. I
Yes,
know
ma'am.
this notation is most compact. When I write it like this, it's very compact. But you have to keep, if you, when you start doing the calculation, you have to keep track of the A and the B. That's all. So this is 0, 0, outer product in A, tensor 0, 0, outer product in B. So this is of the form 0, 0, A, tensor 1, 1, B. Actually explained this earlier also in the lecture.
Yeah, yes, ma'am. Yes, ma'am. I got it.
Got it? Okay, good. Yeah.
Thank you. Yeah, thank you, ma'am.